when we move on with our own business. So the next time of agenda, let me see whether it's good enough for us. Yes, good enough for us. This is an example, I think.
For this video. But since making that piece of content, so many things have happened, and the explosion of this movement has only accelerated and gotten bigger.
Okay, back into business. In the business, we are talking of the Kaplan turbine. We have talked about, we've talked about the Francis turbine. Now we talk about the Kaplan turbine. Okay. Now, what is this guy called the Kaplan turbine? Let me say that this is a turbine which was invented by a gentleman who was a professor, engineer, Victor, not Victor Desmond, or else you start thinking he's closer to the turbine. He's not Victor Desmond Tutu. This was a professor, engineer, Kaplan, who came up with this kind of a turbine. This is an axial flow kind of a turbine or reaction turbine. And under this, we have two types. We have the propeller turbine, and we have the Kaplan turbine itself. In this, fluid enters radially, and I believe it leaves axially. And as a result, it is referred to as a mixed flow turbine. Professor Victor Kaplan modified the propeller turbine in 1913, whereby he designed the runner. Okay? He redesigned it in such a manner that it ended up with what we call adjustable blades. Okay? And for this, he did combine what we call automatically adjusted propeller blades with automatically adjustable wicket gates, what we call wicket gates. We get to know what wicket gates are for the sole purpose of achieving a higher efficiency, which is not achievable with other types of turbines. This is a low head turbine. It can operate with as little as 5 meters. That's the beauty of it. But it has a very high efficiency. The only drawback with it is that it requires a lot of water to run it. That is the Kaplan turbine. In 2017, was it 2017 or 2016? I traveled to Vienna in Austria for a certain project. And when I went to the University of Vienna, Technical University of Vienna, I wanted to see from their Hall of Fame whether they placed Victor Kaplan somewhere. Because I told the Austrians, this gentleman came up with one of the most efficient turbines, which is being used world over. These guys told me this fellow came from a very small town called Creeds at the border of Italy, at the border of Italy and Austria. Because Austria is a little bit north of Italy. And they were associating him with that small city where he came from, but not the amount of work that he did, Victor Kaplan. This top turbine has 2 vanes, and these vanes are attached to what we call the hub or the boss. It is made in such a manner that angle theta and phi, those angles can actually be adjusted when the turbine is in operation or when it is in variation. Or rather, sorry, when it is in motion, not in variation. Like I've said, the blades can be adjusted automatically by means of what we call a servo motor governing mechanism. You only need to adjust it with a touch of a button. And then from a touch of a button, you can achieve what you want with this type of a turbine. Like I've said, by changing those angles of the runner blade, depending on the load condition that exists. And that is the beauty of the Kaplan turbine. If you can make those kind of changes, depending on the loading condition or varying load conditions, you discover that it is the only one which can operate in such a manner. And that's why it has an edge over the others. So when I say that it is a better turbine as compared to others, that is not a misnomer, or it is not a byword. It is actually a reality. The other drawback with it is that it's expensive. And I told you the only place I saw where they seem to have been installed was Kiambere. Kiambere was a project either sponsored by Kuwait or one of the Arab nations with the oil dollar. No wonder they decided to put the Kaplan turbine. It's a small, beautiful thing, giving you a lot of good stuff. I've told you there are two types of axial flow reaction turbines. And these ones, you either have the Francis, not really Francis, but you have the propeller type, and you can have the Kaplan type. I told you between 5 to as low as even 30 meters. Sometimes you find up you can have enough speed to run the turbine when you subject it to loading. And that's why it is a very efficient kind of a machine, in the sense that it can give you an efficiency of up to 92%, more or less. It can be able to give you that. Okay? There's a bit of similarity between the Francis turbine and this turbine, and that's why the only thing Kaplan did was to redesign the runner and to come up with a method whereby adjustments can be made on the blade angles when the turbine is actually turning or when it is in motion. Okay? Otherwise, that gives it an edge over the other types of turbines. Okay? I also told you that it has what we call adjustable wicket gates, so that you can be able to achieve that high kind of an efficiency as compared to other types of turbines. This is a good example, a cross-section of the same. Okay, you can see the positioning of the of the moving blades. You can see the positioning of the guide blades. It has a screw casing, just like the Francis turbine. Though that Francis turbine, you look at the screw casing, it is more of a volute kind of a casing as compared to what we have for this type of a turbine. You look at the drafted tube, it is more or less horizontal as it leaves the turbine to join the tail race. This is unlike the situation where when you look at the drafted tube for the Francis turbine, it's more or less like vertical as it joins as it joins the tail race for water to exit from the turbine after it has been put into use. And that's why you look at it, sometimes you find that it has a lot of similarities between itself and the Francis turbine. It's more or less like you operate on the same principles, except those minor changes which Kaplan came up with to make it more better or more efficient as compared to other types of turbines. You can see the vertical shaft. You can see the flaring of the draft tube, which is horizontal, and the positioning of the moving blades on the boss, or what we call the hub. And then from there, you can see the cross-sectional part of it, the part of it which looks like the Francis turbine, though not quite. They're two different things. Okay? And with 3 to 30 meter heads, we can develop a speed of 60 to 200, more or less, revolutions per minute. Now, this is still the same Kaplan turbine. You can see the details in red. How water comes in. Water comes in through what we are calling the guide blades, or through the moving blades, okay? And then out, and you can see the attachment of the blades, or guide blades, on the hub, or what we are calling the boss. Still, these are details. You can see the governing mechanism, okay? It has got blades attached to it. There's a turbine shaft regulating rod. You can see the positioning of the servo motor and the generator shaft. On the side, you can have the generator shaft, and you can see the positioning of the servo motor. There is a turbine shaft and the operating rod, the crank and the cross head of the same. Then you have more details of the boss, or what we call the hub, with an attachment of the runner blades. You can see the attachment of the runner blades to the boss or the hub for the Kaplan turbine. Still, this is the same for the hub or the boss, and depending on the shape of the blades, it can give you low or it can give you a high performance. But that depends on how the blades are actually shaped or positioned on the hub. Still the same machine, like you've been able to see before. I've blown it up for you to see the details. You can see that someone can be able to access it either through a lift or through a ladder. And you can access some of the component parts, of which for you to make installation or remove something for repairs, you need those giant cranes to remove it. And then you do the repair and you return it. In Canberra, I saw the way they removed it using heavy cranes so that they could be able to do welding to fill in the pitted part portions after cavitation, which was not a very nice thing to see, and especially with such a huge kind of a machine. Still, this is the boss in isolation and the fitting of the blades. Okay, you place there and you can see how they are actually fitted. This is not something you can lift with your own hands. You need a giant crane to be able to hoist it, or even to detach it from the main board of the turbine with the shaft, and even fixing of the blades. You need some kind of a crane which can be able to lift them, and then you fix them to the boss or the hub. Otherwise, it's a very giant thing. If you come across it, it is not just small like you think. It is bigger than big. Let me say that. The hub or the boss. Still on the same, you can see the more details of the same when it is being hoisted using a giant crane not with the ropes this time, but with the strong chains which can be able to hold it or hoist it in the air before you can be able to place it where it is supposed to be. This is another part of it Okay, the way it is placed in horizontal format. Okay, you can see the positioning of the runners, the positioning of the boss when you cut a cross section through it. But this is at a smaller scale as compared to what you are likely to encounter. And you can see the ladder provided. You can access most of its paths through that. You can walk through down and check one or two things. Okay, when it is off. And you can see the power it will develop, sometimes up to 85 megawatts. It's a very efficient machine, but I told you, it requires a lot of water. Low head, but a lot of water to run. Okay? Now, when it comes to the working of that, the triangular inlet and outlet, or the inlet and outlet triangular diagrams, they will look more or less like what you had for the Francis turbine, where you have the inlet diagram up and the outlet diagram. You have it down there, but when you are solving problems relating to this, especially when it comes to your computations, you should first and foremost come up with these triangular diagrams. If at all you'll be able to relate what you are doing with what is happening at the inlet and at the outlet. Okay? When we look at the discharge through the Kaplan turbine, the discharge is more or less like it is for the Francis, because Q is equals to pi by 4 by d squared minus d2, or d squared, d2 squared minus d, lower cases, squared times vf, where d is the diameter of the runner, and a small d is the diameter of the boss, or the hub. Of course, Vf is the velocity of flow at the inlet. Okay? So what are the working proportions of this type of a turbine? Speed ratio is due by square root of 2gh, which is 2.09, while the flow ratio is Vf by the square root of 2gh, which is 0.69, while the specific speed is n square root of p by h raised to power 5 upon 4. Where in this case p is the power, which is equals to w q h eta, which is the same as rho g q h eta for efficiency, which is normally what we do for the turbines. Otherwise, let's see how this one works and how we can be able to compute what computations we can undertake in its design. We have an example that a Kaplan turbine produces 50,000 brake. Brake is B-R-A-K-E, not brake, the other brake. Brake horsepower under a head of 20 meters with an over efficiency of 90%, yes, while the speed ratio is actually 2, and the flow ratio is 0.5, while the ratio of both diameter d by d is a third. Okay? Now, in this, you're supposed to estimate the diameter of the boss and the turbine speed. Now, what is this thing we are calling the brake horsepower? Okay? When we talk of the brake horsepower, it's an imperial unit or imperial power used. Okay? Power at the shaft of a turbine. Okay? Or we can say it is power which is equivalent to 1 horsepower, maybe in SI units. Call it brake horsepower, but it's an imperial unit. Okay? The brake horsepower differs with horsepower only in relation to amount of measurement that is you are undertaking, because horsepower will measure the power generated by an engine, for example, while brake horsepower will measure how much of the power produced, for example, by an engine is sent to the wheels or is transmitted to the wheels, which in simple terms can make a car accelerate or make a move. Okay? Otherwise, when you talk of a brake horsepower in equivalent, it is equivalent to 0.98 times of, or 0.99 times of a horsepower. Okay? Let me put it in for you, because I know that I'll be able to share these notes instead of me talking out here. Let me say, for example, one bhp. Okay, let me call it 1 bhp is equal to be precise, it will be equal to 0.9683 HPs. That is where they differ. Otherwise, some people would like to talk of brake horsepower when they are simply talking about horsepower, because they believe that they are more or less, or they are almost the same. But we normally say the difference is quite slight. It's a very slight difference. Something less than, I don't know whether it's 1% or 10%. Okay? And I believe with that, you'll be able to know what exactly you are talking about. Now, having seen that, is it possible for us now to estimate the diameter of the boss and the speed of the turbine? That is what we are looking for. By taking d by d, small d for the boss diameter and a big D, okay, for the larger diameter, which is associated with the runner. And in this case, that ratio is equal to 1/3. If there's a head difference, I believe that is what we had. It has a head of 20 meters and an overall efficiency of 90%, eta naught of 90%. H 20 meters, and the VF by square root of 2GH is 0.5. Eta naught is 90%. U by square root of 2GH is 2.0. Then from this, we can say VF is equals to 0.95 or 0.5, sorry, by the square root of 2GH, which is equals to square root of 2G by 20 by H times 0.5, and that translates to 9.9 meters per second. If we do the same for U, because that was for VF, U is twice square root of 2GH, which is twice square root of 2 by 9.81 by 20. And that translates to 39.6 meters per second. They're very simple things. Now, HP, or break, or rather, eta naught equals to BHP by WHP, input by output, because we have said break horsepower is that which is transmitted to the system to facilitate for movement, or the end result of the power which is generated after the input of so much. Input is rho GHP or something like that, or rho GH times P, or rho GQH, okay, divide by 750, because you're converting that into horsepower, which is equals to 0.9, because the efficiency is 90%. That tells you Q from that equals to, because we don't know Q, will translate to 212.4 cubic meters per second. That's a lot of water, you can see. A lot of water, you can see, compared to the other example where we're getting 0 point something, 8 something for the Francis turbine. This one is in hundreds. And given our Q is 212.4 cubic meters per second, we know that Q equals to pi upon 4 into D squared minus small d squared by VF. And that translates to, because we're looking for the diameter of the boss, that translates to that equation being rearranged that way, because the boss diameter is 0.33 times of D capital squared. When you subtract that and you work on it, what exactly are we getting from 212.4? We are getting D as 5.535. That is for D for the runner diameter, and the small d is 0.33 times of D, which is 0.33 times of 5.535, and that translates to D equals to 1.83 meters. If we take 2 meters, 2.0 meters the diameter of the boss, we can round it off to that. Then that tells us D equals to, 1.8 times 3, which is 5.5. You can see it is getting us back to that. Otherwise, U is given by pi dn by 60, which is pi by 5.5 by n by 60, which is equals to, we say 39.6 equals to pi dn by 60. When we try to make n the subject, we're talking of 39 times 60 by pi 5.5, and that translates to 137.5, round it off to 140 revolutions per minute. Good, that was example number 1. Example number 2, I'm generous. A Kaplan turbine has an outer diameter of 8 meters and an inner diameter of 3 meters, developing 4,000 horsepower and a head of 12 meters. The discharge through the runner is 300 cubic meters per second at a speed of 8 RPM and hydraulic efficiency of 95%. Determine inlet and outlet blade angles, determine mechanical efficiency, overall efficiency, given D is 8 meters and small d is 3 meters, BHP is 4,000 and N is 80 RPM while H is 12. Q in this case, you are given as 3,000 or 300 rather, cubic meters per second. Eta hydro or hydraulic efficiency is 25%. You can see the solution of that is just like a repeat of what we have done. Okay, so a repeat of what we have done. Maybe a small correction here to say what phi equals to VF1 by U1. You can say that which is 6.95 by 3.51, and that translates to 0.2074 arctan. That gives us 12 degrees. Otherwise, VF is 6.95 meters per second, while phi is 12 degrees. These are very simple things to understand. I need not dwell so much in this because it is just solved like the other one. Okay, the only thing is what the mechanical efficiency, eta mech, is BHP by W by G by VW by U by 750. You put that together and you're getting 87.7%. Say it is 88%. But remember now, if you don't know, but I'll let you know, overall efficiency, eta naught is equals to eta hydraulic times eta mech, 0.95 times 0.877, which is equals to 0.83 times 100%. And that translates to 100.1%. And for that case, we are taking 83%. Okay. Still working on the same. I have another example for you on the same. The following data is for a Kaplan turbine runner diameter unit power equals to what? Developed by turbine under a unit head. Okay. And a unit head discharge, unit discharge is equals to that. Working at the head of say 1 meter, unit speed is equals to that. Theoretical speed of a turbine working under unit head equals to that. You estimate the runner diameter, just the same like the other one. I'm sure you'll be able to follow this without much ado. Also for similar turbines, I touch a little bit of that. I didn't want to take you through that because you have done dimensional analysis. Let's talk of similar turbines. N1D1 by square root of H1, it should be equal to N2D2 by square root of H2. We are talking of 120 for that speed times 1 by square root of 2.5 equals to 24. And then from there, we can get D2 equals to 0.14, which is 140 millimeters. Q1 by D1 squared by square root of H1 equals to Q2 by D2 squared by square root of H2, leading us to 100 by 1 times square root of 1, which is Q squared by 0.14 squared times the square root of 2, 5, telling us that Q equals to 100 times 5 times 0.41 squared, and that translates to 9.94, meaning the discharge Q2 is 9.94 cubic meters per second. So these are simple examples. You can be able to follow. Just like for centrifugal pumps, we can have a look at the performance and selection of turbines. Yeah, it is there in your syllabus, but I'll not say much about this because you look at unit speed versus the discharge, or unit speed versus the overall efficiency, unit speed, blah, blah, all that. Then you can look at the units discharge versus unit speed. You can have a look at the way the performance curves look like for actually turbines. It is the same principle like it is for centrifugal pumps, not so different. The only thing I've told you and you should remember is that a turbine is the opposite of a centrifugal pump. Okay? Otherwise, just have a look at this when you get the notes. Then you can see another example. I've put in other examples for others, like for Francis turbine. The following data refers to a Francis turbine. Also look at that. I've also solved it for you. Okay? I've solved it for the Francis turbine. I think I must be having one for Pelton wheel, which I've also solved because I wanted you to see the difference between what happens with the Francis and Kaplan and the Pelton wheel. I've solved that also for you. Unless you have any questions, still the same for that, all the way up to the end. I've done that. And working with turbines, I've determined the number of buckets from empirical relation number of buckets, Z equals to 0.5 D by D plus 15. And you can see where we are getting 20.55. Take 20 buckets. That is a bit more even. Width of the bucket is 4D, which is 4D by 0.25, 1.12 meters. Depth of the bucket is 1.2D. Remember those details? I think I gave you when I was talking about the Pelton wheel. And that translates to 0.336 millimeters or meters, which is 336 meters. I have another one. This is a double jet. I think I'd given you this one. A double jet Pelton wheel. We solved this one. But there's nothing wrong if I repeat it. It's for your own good. And I've worked it out all the way up to the end where you got 14,035 horsepower. Working the turbine still on the same until you got diameter for D. Okay. From inlet, which one is this? See the same example. I think it is maybe a different example. What I don't know is where the words are. Okay. Let me see whether this one makes sense. I don't know whether the question which I decided to solve before I could check whether it is a continuation of this. It could be a continuation of this. Please find out whether it's a continuation of this. Okay. If it is not, you just ignore it. But it is likely to be because I can see CV of 0.46, which I have in my data. Speed ratio of 10. Yes. So it's a continuation of the same all the way until you can be able to get force exerted by the jet, which is 15,566 newtons. So have a look at that. And when we talk of the synchronizing speed of the same, I think it's the same problem being solved. As the jet ratio is 10, I think it's the same, yeah? Just have a look at that up to the end, and that marks the end of our discussion. Any questions? Any questions as I share these minutes? They are not minutes, they are notes. As I share these notes with our good guy, Desmond, Victor, but not Victor Kaplan. Desmond, you are not Victor Kaplan. Get to know that. Usijipatie hiyo jina. Kaplan Turbines. I looked for his name in the Technical University of Vienna. And those Germans, Austrians are Germans. They tried to belittle him. And I told them, gentlemen, this guy came up with a very nice, efficient turbine. But I don't know what they'd done in school. Because when I talked about turbines, they didn't seem to understand. There's only one professor who was a nuclear physicist, who was a nuclear scientist, who told me he has spent years building nuclear power stations. He told me, my friend, I've spent many years building these nuclear power stations in the world. Very hedged. And we became friends because we found a common ground to talk. He told me there's an unfinished project. And I told him that one we shall talk about it as we try to finish, because I'll be part of the finishing team. We shall finish that on the payday. Nasikia Desmond. Desmond, do you know the payday?
Yes.
Which is the payday? I've shared with you the notes. Do you know the payday? Which day is the payday? Do you know the payday? Do you know the payday, Victor? El Bethel, do you know the payday, though you told me you are a Kenyan?
I'm not sure of the one you're referring to.
Nimekuongopa. Hey, if you're a Kenyan. Nimekuongopa sana. Even if we make the trip, I'll be scared of you, but we shall talk. Unasikia hiyo Bethel? We shall talk. We need to talk.
We'll talk.
Yeah, I'll give you a chance we talk. Bora hutanikandamiza.
I'm a Kenyan, not Ruto.
I really fear you when you say you are Kenyan. Anyway, I don't know how many slides this one has. It has 9 slides. It's a small thing. And please allow me to talk about this. This finishes our syllabus. Completely. Now, the next last thing in our syllabi is talking about power transmission through pipelines. You guys are becoming too learned. My friend, if you catch this, you'll be very learned. Okay? Very learned. Even when you go for master's degree, you find it very easy. Okay? You will find it very easy. Now, what is it about power transmission? Okay? When we talk of power transmission through pipelines, what should come into your mind? This is, you transmit power through pipes by whatever liquid is flowing. Those liquids, those pipes, like water, for example. The power which is being transmitted will depend on Q, that is the rate of flow, and the total energy per unit weight of the liquid. Now, this is a principle that is used in various applications, including, that is, hydroelectric power stations, where water from a reservoir is conveyed through a pipe to a turbine. You can see basically it is more or less like the same principle which was borrowed, so that we can talk about turbines. Okay? I've told you that one of the factors which affects the transmission of power is the liquid being transmitted and the rate of flow, that is Q, or the volume of that liquid which will pass through the pipe per unit time is quite a factor. Otherwise, when there is a higher kind of a flow rate, that will lead you to a greater power transmission. Okay? Otherwise, this will depend so much on the total head available at the pipe inlet. That is for both potential and kinetic energy, if you care to look at it that way. The other thing is that you look at the head laws in that system. What is your HF? Energy that you lose because of friction between the liquid and the pipe walls. This actually reduces whatever head is available at the outlet. Otherwise, what do we say? We know power is given by rho GQH. That is a fact, where rho is the density. Let me put that equation here. Okay. Let me say we know, and if you didn't know, you know. We know that P, or power, is equals to, we know that, not the, power equals to what I'm going to insert in this. And I'll say this is equals to rho G Q H. It's equals to rho G Q H, where rho is the density of the liquid. Okay, where rho is the density of the liquid. Let me see whether I can squeeze this at the corner so that I say where rho, where with colons, rho, which I borrow to this. Let me borrow the whole of this so that I will know how to deal with it. Where rho, where is that? Wanapotea bure, where rho hapa. Where rho in this case is equals to density of the liquid. Let's put it that way. Rho is the density of the liquid, or liquid density of liquid. Yes, of course, you know the units of the density. G is your gravitational acceleration. your gravitational acceleration. Okay. I'm treating it with addition. Acceleration. Yes. And Q in this case, you see the way I'm treating it. Q is the flow rate. Flow rate. And H, if you want to, H is the total head. What am I trying to come up with this? With this kind of a setup. H is the total head. All this, let me put them in a better way. And I change this to FB. And of course, I try to make them bold. Yeah, that is good enough for us. So from this reservoir, the total head is H. You can see that. From the reservoir, the total head is H. Then from A to B, there is movement of the fluid with a velocity V. While the total length, this is not properly put. It has to be from the exit, where the exit is. The total length of that pipe is L. Okay. What is the maximum power being transmitted through that? Okay. For that to happen, maximum power being transmitted, let me call it P max. P max should be equal to, allow me to carabat this for you guys, to be the best in the world. If you're careful. I want you to like hydraulics. I liked it when I was a student, and I did it at for master's level. I had a unit in hydraulics. And even then I liked it because I used to score good. So for power maximum, I'm sure you not miss that. Head loss due to friction. Head loss. Head loss due to friction. Due to friction should be a third of that, of the total head. Should be, actually, let me put it here. It should be 1 upon 3 of H. Okay? 1 upon 3 of H. Let me put it that way. That's what it should be. If that will happen. This is, in other words, that is i.e., I'm saying i.e. HF equals to, borrow from here, to put here, where I'm saying HF equals to H upon 3. That's what I'm saying. Head loss equals to that. I'm sure you didn't know that. but you should know that from today. Kwani mlikuja kufanya nini if you don't get to know this? Masi Mumbi, what did you come to do when you left home? Kweli waambia unaenda kufanya nini? Kuambia tutakutana. Okay, basically that is what we are saying. The head laws in that between A and B, the velocity of V, for power to be maximum, that is the cardinal thing about that. Okay, actually I've talked about it in this. Meaning, the head which is available at the outlet of the pipe should be the head at inlet minus the head loss due to friction. So we are talking of H minus HF, okay? And we have said HF is the third of H, equals to H minus 4 FLV squared by D2G. Weight of water flowing through the pipe per second. How much is that? The weight of that is density times Q by volume of water per second, which is rho G times area times velocity, which is rho G by pi D squared upon 4 by V. Otherwise, power transmitted at the outlet will be the 1 times the head at the outlet. Okay? We'll come to that. Times the head at the outlet. Weight of water per second, which is rho G AV by H. Okay? Times rho G AV by H gives us power transmitted through the pipeline. Now, when you look at whatever is coming from a reservoir, which is at a high altitude, or what is coming from Sasmua Dam towards Nairobi, that is elevation conveyed by a pipeline. If you fit on it an impulse hydraulic turbine, which in this case is a Pelton wheel, in an hydroelectric power station, the hydrostatic head of water will then be transmitted by the pipeline. And when you analyze the efficiency or the power transmitted under this kind of a situation, what will you be able to get? Because the potential head of the reservoir is H, and the difference in water level between the reservoir and the turbine, or the elevation difference, you can be able to get that. So, head available at the pipe exit, be HE minus equals to H, or head at entry will be equal to H, which is equals to HF, but not exactly HF. HF is what remains. Sorry. HF is what remains after the friction losses are taken care of. It cannot be the same, I think. I will not agree with that statement which I made here. I don't think I agree with that. Okay. Okay. Or let me say is equals to HF. Or let me return that. I want to see the idea I had when I brought it there. For my original thoughts. Okay. Where HF is the loss of head in the pipeline due to friction, assuming that the friction coefficients are constant, we can say HF is given by KQ squared, where Q is the volume flow rate, K is the hydraulic resistance of the pipe, that is your 4FL by D. Yes. And therefore we can say power available P at the exit of the pipeline then will be equal to rho GQ H by eta, because you have said we can fit hydraulic turbine at the end, which is equals to rho GQ into H minus KQ squared, which is rho GQ or rho G into HQ minus KQ cubed. For power maximum at a given head, H, it will be dP by dQ equals to 0. I like that now. I think I'm on my right track. It's equal dP by dQ, whereby H minus 3 times of KQ squared equals to 0, leading us to KQ. I don't like that. Let me see whether I can put in another symbol. Oh dear. Oh dear, oh dear me, oh dear me. I don't like that symbol. Let me put another symbol because I've activated it. I want to put that symbol. Okay. Where did it go? Yeah, it's here. Oh dear. Where is this one misbehaving? It will not misbehave. I want to bring it here. Yeah, to imply, yes, KQ squared equals to HF, which is equals to, now you can see that, which is equals to H by 3. You see that? H by 3 by D squared P by DQ squared, which is always negative, showing that P has only one maximum value, not a minimum with Q. That is, so from H minus 3 times of Q by Q squared equals to 0, the maximum power is obtained when H over 3 of the head available, the source, that is the reservoir, is actually lost through friction when the flow is taking place in the pipeline. Otherwise, efficiency of power transmission, eta efficiency, is given by rho GQ into H minus KQ squared by rho GQH, which is equals to 1 minus KQ squared upon H. Therefore, efficiency will be equal to unit for trivial cases of Q equals to 0. Otherwise, for flow to commence, then eta hence, eta P is, oh my, I don't like the language I'm using. It is monotonically decreasing from Q. I don't like that. From Q to a maximum value of unit to 0. What do I mean by that? When I say that it is monotonically reducing. What I mean by that is that the way it will be changing, or it will not be varying, okay, in appearance. I don't know. I think I don't like that. Let me take it from maybe monotonic, what we call monotonic power supply. When we talk, for example, if you can remember a bit of the electrical, when you talk of the monotonic power supply, is where you find the output voltage will keep on increasing continuously, or it may remain constant during power or on startup and there will be no drop off, there will be no fluctuations. This is quite crucial when it comes to electronic devices. But when it comes to monotonic power, let's say for monotonic power transmission, what does it portend? When you talk of that, it is a way of saying that power will strictly decrease as a function of Q from a maximum value of a unit to zero. And therefore, for the zero value, now in this case, we're saying eta P will correspond to the situation that we have been given, that or given by KQ squared will be equal to H, or K or Q equals to the square root of H over K. That is possible, where H is the available reservoir, or is the head available at the reservoir, and whatever friction head is getting lost with the flow through the pipe